Thank you, Chris, and thank you very much for inviting me to come down and speak to you today. I'm Professor Noakes. I'm in the School of Civil Engineering, just up the road at Leeds University, so I haven't come very far at all. I'm going to talk about something a little bit different. I'm going to start delving into some of the technical challenges around making buildings sustainable. Particularly, I've worked in the area of ventilation and indoor air quality for a long time and have quite a big research group in that area. And I want to think about this in terms of human aspects of ventilation and just show you some of the work that we've done in this area and get you thinking about how the human side of it matters in sustainable buildings. So we tend to think about ventilation as a building function. In fact, we tend to think about sustainability in terms of building. We measure emissions, we measure carbon, we measure energy. Okay? So we focus on the building. We also think about that in terms of ventilation. So often when you specify ventilation, we specify a temperature, we specify an air change rate. If it's working well, we measure the building. But what about the people? Okay? So the whole point of ventilating a building, or for most buildings, the primary reason we do it is because there's people inside it. Most of you don't really care about, say, your garden shed. There's nobody in there. Okay? The building like this, we care about the ventilation because you're in here. And that's where it gets difficult. We've probably all experienced this one here. Is this one poor design, or is it because those people in that room all feel different, are all variable, or experience things differently? Everybody experiences things differently. Everybody has their own different needs. Some people are much more susceptible to things than other people. And we're also very poor at sampling the air. So if I asked a sort of show of hands around the room, is anyone a bit hot in here? Mm-hmm. Yeah, a few? Anyone a bit cold? Yeah, so we've got 2 in here. Can anyone tell me what the temperature is in here?
About 23.
You can do a reasonable guess, but you don't know. Yeah? Okay. Can anyone tell me what contaminants are in the air in this room? CO2. CO2? Anything else?
Ozone.
Possibly.
Particulates.
Particulates. Are there any infectious microorganisms in here?
Some from the carpet.
You're guessing, but you don't actually know. So we're reasonably good at saying, are we comfortable? We're not very good at actually saying what is really in here. So we're poor at sampling. And we affect the air affects us, and how we behave changes things. If you think about this in a little bit more detail, we're all a heat source. Every single one of you's got a little plume, about 0.2 metres per second, rising above your head of hot air. So you're changing the airflow in here, regardless of how it was designed. Every time we walk along the corridor, we take a wake behind us, we drag air, we drag contaminants and things with us. We breathe. So we all introduce CO2 into the room. Some of us, sometimes, introduce other contaminants. If you've got flu, you could leave, possibly. Might be a good idea. Okay? We introduce things in there. And we mess things up. You all do it. We go and open a window, we open a door, we do things that make us more comfortable. Some of those things were as the building was designed. Some of those things were perhaps not what the designer intended. Okay? There's a big body of evidence that the indoor environment affects people. Thermal comfort, there's quite a lot of work on. So this is from Sipsey guide. This is a graph which shows multiple studies looking at the influence of temperature on people's performance. What you can see is every single one of these lines is a different study. Every single one of these lines shows something a little bit different, but there's a common consensus in here that if it's too cold or if it's too warm, the performance of those people in that environment suffers. What about CO2? We tend to think of CO2 as a proxy for ventilation a lot of the time, but there's an interesting debate going on about whether CO2 is a pollutant in its own right. It certainly is at very high levels. Is it at lower levels? This is from a US study where they put CO2 in environments, pure CO2, up to levels that you might see in a building. So you do see 2,500 ppm in buildings when they're poorly ventilated. And they showed that it impacts on decision-making performance. So maybe, we need to think a bit more about even those most basic of pollutants like CO2. And this is my favourite subject, airborne infection. So I've worked a lot around hospitals and hospital design. And I've put this on here to get you to think about how complicated some of these things is. So think about the process of transmission of infection. You have a source. Anybody who's got children knows this one very well. But that might be a cough, a sneeze, it might be an environmental source from a shower or something. That might be infectious microorganisms, they're released in droplets. Those droplets have a size distribution, they have a location, they have a momentum, they get put into the air. What happens to them depends on the local airflows in that environment. It doesn't depend on the global design of the ventilation in the building. It depends exactly what happens locally. Do they stay in the air? Do they get vented out? Do they deposit onto a surface? And then people get exposed to them. And even that is very complicated. Do they breathe them in? Do they impact it in their nose? Do they touch a surface? All of these routes happen. And the whole process is incredibly complicated because it depends on the pathogen and the disease characteristics involved. How flu spreads is quite different to how TB spreads, for example. They depend on behaviour. People behave differently. Some people will be very close to each other. Some people shake hands. Some people will sneeze. Some people will cover their mouths. Very different. And it depends on the flows, which of course is my world, the engineering of that environment. Okay, so it's incredibly complicated, this. And this is why I think we need to think a bit more about ventilation in buildings, because we focus very much on the bulk air. We talk about air change rates, but we actually need to go back a bit more and say, well, what do people need? Not what does the building need. What temperature do they need? What flow rates do they need? Where do they need those flow rates? What quality of air do they need? Does everybody need the same? Or do we need some different things for different people? How much do these parameters affect your health and your productivity? It's a very easy question to ask, an incredibly hard question to answer, because everything changes, everything's variable so much. And time, okay? We tend to think of ventilation as a very steady state thing. We have a target, we want to fix a temperature, we want to fix an airflow rate, but they change over time. We need to understand how that changes and how that matters. And if we can answer that, which is hard enough, we then need to think about how do you bring that into design? How do you have the right tools and the right metrics that consider people, consider the existing solutions, consider new technologies in there? So just to give you some examples of some of the work we've been involved in, this is a current project. It's called Refresh. It's an EPSRC funded project between Leeds, Southampton and Reading. And we've done a lot of work on natural ventilation and the influence of urban design on natural ventilation. This thing here is called the Silso Cube, so it's a metal cube, building sized. It's got pressure taps around the sides of it. It's got openings on the front and rear face, so you can do ventilation inside it. And we've looked at it on its own, and with an array of buildings around it to look at the influence of those other buildings on their flow there. We've got a full-scale experimental data set from about 9 months on this site, and we've got computational fluid dynamics where we've looked at the airflows around these buildings. And I'll show you a couple of results from the computational fluid dynamics. This is on its own. So we looked at different flow rates, different flow directions, onto this building. This is where you put the wind normal to the window, and we don't rotate the wind, we rotate the building, so this is where it's parallel, so the windows are on the side in this case. When you've got the wind sort of hitting the window and going straight through the building, what you get is a strong jet through the building. You get a very well ventilated building, but you get quite a variation in the mixing that happens inside that building. When you change the angle, you see a different pattern in here. You lose that jet, what you get is a pulsing flow, goes in one side and out the other. And as you turn the wind angle, you get a critical point where you lose this jet and you change to this flow. But what's interesting is when you surround your building with other buildings, it's not quite so easy to see, but here's our test building, the two look very similar. So that urban environment, what it does is it reduces the overall ventilation rate, but changes the variability and stops it being quite so dependent on the wind direction. And from this, we can find out the pressure coefficients that allow you to design that ventilation better and understand the flow patterns that you might see in those buildings. Another one we've been looking at is around hospitals. Big spaces in hospitals. What do we mean by ventilation rate? In a hospital, we're supposed to have 6 air changes an hour. in a hospital ward. So this is a big ward. It's a naturally ventilated ward. This is a computational fluid dynamics model. 6 air changes an hour go in one side, 6 air changes an hour go in the other side. But if you look at what happens where the people are, it's quite variable. You can plot the local air change rate and you see that some of those people will experience 6 air changes an hour, some will experience more, some will experience less. So is that 6 a useful number at all, or do you have to understand what's actually going on? And one of the things we did in here was look at the distribution of the air change rate and say, well, actually, 6 is here. The most common air change rate is lower than 6 that these people experience. When you change the ward design, you spread that distribution out. You get a different answer. So understanding that helps you understand how well your ventilation is performing. We also then said, well, can we link what's happening in terms of ventilation? If we provide more ventilation, it's going to cost more energy, it's going to cost more money. But does it make things better for the people? And this is a specific case looking at infection in hospitals. And can we look at the trade-off between increasing the ventilation rate to reduce infection transmission versus the increasing cost because of that? And it's a hypothetical scenario. What you discover is it's quite easy to put some money or some value to the energy cost of ventilation. It's a lot harder to put some money to the cost of an infection. What was interesting though is even though this was quite theoretical, you find the sweet spot. The sweet spot is where these lines cross. And the sweet spot is somewhere between about 4 and 7 air changes an hour. And the guidance says 6. So maybe the guidance isn't far off right. The last one I want to mention is new technologies. So we tend to focus on air quality being solved by ventilation, temperature being solved by ventilation. But you can decouple that, and you can introduce technologies to filter the air, to clean the air in certain ways. There's a big body of research growing on this. There's a very poor understanding of how these sort of devices actually get used in practice. So there's areas of things that we're working on around these. But potentially, some environments, we can solve air quality problems by these kind of cleaning and disinfection technologies. So just to finish up, because I know everybody wants a coffee, some of the things we think we need to think about in research. We know a lot about indoor environments, but I don't think what we're doing is good enough, and certainly isn't good enough for the next generation of sustainable buildings. Ventilation, we can't think of it anymore as just a bulk parameter. We've got to think about how we deal with it for people, because at the moment we're wasting energy and we're not creating environments that are good enough for the people in them. So we need some better understanding in here. We need to know how buildings and the air quality actually affect people, and getting that evidence is hard. It requires a lot of interdisciplinary working. We need to understand how things change with time. Rather than aiming at a steady state, we need to understand how it changes with time, and therefore where there might be advantages, how we can use these transients to get better buildings. And we also need to understand much more about, if we're thinking of new technologies, how and where can they be deployed? What's the pros and cons of them? And to evaluate them both in a human and social context, as well as just the engineering or the technical solution. So I think we also then need our sustainability and design metrics to give us an equal weighting from the energy and the emission side of things to the human aspect. Because ultimately, we won't get better solutions until we really think about the people. And the last one I'm going to leave you with is a little model just to show it off. So this is a real-time flow model of a hospital ward where you have 4 people in here and a rather short doctor. It's coloured by temperature, so you can see the thermal plume rising on this above this doctor. This is where the ventilation air comes in, and you can see the interaction ventilation air and the thermal plumes. You can move the positions of everything around in there. It's a fully interactive real-time model. It's a very much a research tool at the moment, but the intention is we'll be able to use this to think about how designs work and whether we can react better in real time rather than just react to environment. Can we predict how environments are going to change? So that was a very whistle-stop tour of ventilation in buildings, but I hope it's got you thinking a little bit about the people in those buildings and how the air in that building matters to people. Okay, so that brings me to the end. Thank you very much.